Good to go? All right. Good afternoon, everyone. Thank you for being here. I'm Amr Abdelgawad. This is Hasaan Waseem, Abdulaziz AlMutairi, and our fourth group member is Rahul Purandhara. And we are here today to present to you our fourth-year design project, which is a conductive hydrogel vest for infant breathing rate monitoring. To start off, we will discuss what the problem is right now in terms of the state-of-the-art that is available right now as well, and how sudden infant death syndrome could be detected, as well as the customer requirements that are needed to provide a proper solution and the competitive advantage that we have in terms of our solution before we go in depth in terms of the design system, the characterization, and the electrical testing that was done on our device. So conceiving a baby could be one of the most rewarding experiences for any parent. Sadly, however, some parents lose their infants due to sudden infant death syndrome, where an infant stops breathing while they're asleep. Sudden infant death syndrome affects a lot of infants during their first year of growth, and it mainly occurs between the first month and first year of development. In the United States alone, over 1,500 infants die every year due to sudden infant death syndrome, and it is considered to be the third leading cause of death in the United States. And as of 2010, over 22,000 deaths occurred worldwide because of SIDS. And these were just the reported cases. This doesn't take into account the number of cases that do happen yet are usually not recorded because of such a problem. And this could be devastating for parents, as they would usually have just conceived their first baby, and a few months later they would find them dead because of that disease. In fact, it isn't considered just any one illness or disease. It's the diagnosis given when an infant simply stops breathing while they're asleep. In the United States alone, of the 1,500 infants that usually die, it mainly affects infants between 1 to 4 months, with 90% of the cases that have been reported occurring to infants less than 6 months old. And almost 800 of those infants usually die because of suffocation and strangulation, and the remainder are usually dead because of unknown reasons that have not yet been investigated. Now, the most relevant and recent story that did occur because of SIDS was for Oliver Carter, also known as Bernie Baby, who was found dead one morning in his crib a few weeks ago because of SIDS. This caused an increasing rally for support in order to try to detect SIDS at an early stage to prevent its development later on. Now, compared to what's available in the market right now, the state-of-the-art shows that there are solutions that can detect SIDS. However, these solutions are usually not reliable, as they are not in direct contact with the body. As we can see on the top, the first one is a detachable sensor that is usually attached to an infant's clothing, and that allows the identification of an infant's breathing profile and their activity. And another sensor uses the state-of-the-art that is also attached to the body. However, these solutions have obvious flaws in them. And the fact that they're expensive, they have short-range connections, and are not in direct contact with the body usually results in a lot of false positive results for the parents, and sometimes they don't even detect as soon as SIDS happens. Now, in order for customers to want to purchase our solution, it has to provide them with real-time feedback. They want to be alerted immediately as soon as a problem happens. Therefore, if an infant breathes approximately 20 to 40 times a minute while they're asleep, then we can consider a breathing cycle to be of approximately 3 seconds, where the cycle would consist of an inhalation and an exhalation. During that time, if the breathing cycle exceeds 3 seconds, then this is the point where we need to send out a distress signal to alert the parents immediately of a problem developing. In addition, it has to have minimal health risks so that it does not affect the infant at all. And the hydrogel that we are going to be using for our system is polypyrrole, which has been shown in literature to have very minimal toxic effects. In addition, it is also used in many biomedical applications as a conductive polymer additive. The third point is that it needs to be durable. It needs to be able to withstand stretching of the vest and the compression of the hydrogel. If an infant usually sleeps from 3 to 5 times a day, then we can consider that the vest would be used for approximately 2,000 times over its lifetime. During that period of time, the hydrogel will be compressed approximately by half of its own size, and the vest itself will be stretched approximately 2 to 3 times of its original size. So it needs to maintain its durability over the period of time that it will be used. In addition, the vest should be lightweight so that it doesn't stunt the infant's growth or impede its movement. And when we used the hydrogel in our testing, we made a sample of approximately 5 centimeters squared with 1 centimeter in thickness, resulting in a total volume of 5 centimeter cubed. That hydrogel is actually very light in its weight. It's approximately 0.1 grams. And when you compare it to current clothing that infants usually wear, infants' clothing approximately weigh between 80 to 100 grams, which makes our solution much more lightweight compared to the current clothing. Finally, it needs to be affordable so that it could be used by the buyers in the market. And when we calculated the cost of manufacturing one vest, we approximately calculated the cost of the chemicals, the manufacturing, and the labor costs, as well as a 25% contingency overhead. And the total cost of such a device would be approximately $70, which is almost half of the cost of the current state-of-the-art in the market. Now, our solution is an innovative solution that could potentially save a lot of lives. It will be a vest with a conductive hydrogel polymer that can detect the presence or absence of breathing as soon as it occurs. The hydrogel vest will expand and contract, mimicking the infant's breathing profile, so that it can actually send the signal immediately to parents, alerting them as soon as a problem happens. In terms of the mechanical aspect of it, the hydrogel will be in an interlock system that will be placed inside of the vest. And at that point, as soon as an infant inhales, the interlock system squeezes on the hydrogel in order to send a signal immediately to keep the parents up to date with their breathing profile. Now, our solution has a major competitive advantage over the other ones in the market. It is actually a contact mode solution so that it's on the infant's body at all times in order to be able to monitor the infant in real time without resulting in any false positive results. In addition, it is going to be cost effective, reducing a lot of costs compared to the current state of the art. And according to the Center for Disease Control, there are almost 4 million infants that are born annually in the United States. And when parents know that such a technology does exist and could potentially save their infants' lives, they would find a lot of comfort in using such a technology. Now, in order to produce our hydrogel, we followed a synthesis method similar to the research article, Elastic Conductive Polymeric Hydrogels and Sponges, where we prepared 2 solutions. One solution had the pyrrole mixed with a 1-to-1 solution of water and ethanol, and another solution had the iron 3 nitrate, non-A hydrate, with a 1-to-1 solution of water and ethanol as well. Both of these solutions were freezed to approximately 0 degrees Celsius before they were individually vortexed and then mixed together to form the gel. The gel forms almost immediately. However, we leave it to age for approximately 30 days in order to obtain a gel with proper structural integrity. And then we solvent exchange it with water to get rid of most of the ethanol before we freeze dry it another time to get rid of the remainder of the ethanol in order to obtain our final hydrogel sample. Now, in terms of characterization, we have tested this sample and performed SEM analysis on it in order to identify its structural integrity. And as we can see, it formed a continuous 3D network of the pyrrole itself, where they formed spherical particles that were connected through pi-pi interactions. And the average chain width for each pyrrole spherical particle was approximately 1 micron in length.
So after synthesizing the gel, we then focus on its electrical performance. In order to do that, the very first thing we did was we had 2 glass electrodes that were covered with aluminum foil to have them conductive. We connected these electrodes to a digital multimeter and placed our gel in the middle. We used manual compression by fingers and applied the compression force for the gel and observed the resistance changes in the digital multimeter. From this analysis, we observed that the gel, when it is not compressed, led to a resistance of around 300 kilo ohm, and when it was pressed, it led to around 200 kilo ohm. So after establishing this knowledge, we created a V-Storm bridge. So the idea behind the V-Storm bridge was to actually monitor the real-time change of resistance of the hydrogel. So in this figure, the RA and RB are supposed to be exactly similar, and we use 100 kilo ohm in our case. RC, however, was the reference resistance, which in our case we use 200 kilo ohm, which refers to the minimum achievable resistance obtained from the hydrogel through the digital multimeter test. And then Rx refers to the changing resistance or the questionable resistance that we want to measure of the hydrogel. As the resistance changes of Rx, the voltage between these 2 points across VB, you can see, they change. The voltage changes, and as a result, this is monitored in real time, and which can be implemented to actually understand the real-time change in resistance as well. I will explain that later. The input voltage that we use throughout our testing and potentially will be used in our final prototype is 5 volts, even though we can also lower it down to even further than that. In order to get good communication, we used microcontroller Arduino Uno. It had 14 ports that could either be used as inputs or outputs, had a 16 megahertz quartz crystal, and had a USB connection that lets it power itself through a laptop and gives us the flexibility to program it using a software. In terms of software, we used MATLAB 2014A and Arduino support package that was available through MathWork website. So after establishing the communication between the microcontroller and the Wheatstone bridge, we evaluated the overall circuit by using a variable resistance box. So in this case, in the very first graph, we changed the resistance from 200 kilo ohm to 300 kilo ohm, referring to the minimum and the maximum achievable resistance observed through the hydrogel. We can see that it generates a step function profile. As a result, however, the hydrogel does not give a step function profile because it gradually changes its resistance. Then we further investigated different increments of resistance. So in the next case, in the next graph, we have a 10 kilo ohm increments of changing resistance, and then the next one has 1 kilo ohm at the bottom left, and then finally 100 ohm. 100 ohm was the minimum achievable resistance obtained, the change in resistance obtained from the hydrogel. However, it is clear that as we go down in lower increments of resistance, the signal-to-noise ratio suffers. So in order to improve that, we use the inbuilt function, smooth function in MATLAB, and we're able to get a sinusoidal profile for all of the analysis that we have done with different increments in resistance. And we were able to get the similar profile for 100 ohm as well, shown in the bottom right. After establishing this, we then focused on frequency, as this is our major goals. We want to know how many times or what the breathing cycle of the infant is. In this case, a breathing cycle refers to a complete change of resistance through the variable resistance box from minimum to the maximum. So in the case of 100 kilo ohm, as you can see in the first graph on the top left, it changes the resistance from 200 kilo ohm to 300 kilo ohm and back to 200 kilo ohm. And we were able to observe significant dominant frequency in all of the analysis that we have done. After this, we evaluated our gel performance. And for this, we, once again, as I mentioned before, we placed our gel between the two electrodes, and then we applied compression by our fingers manually. And we're able to monitor the changing voltage in real time, as shown in the bottom left graph. Since we know the output voltage, which is VB, and we know all of the rest of the resistance that we used for the Wheatstone bridge, we can measure the Rx, which is the resistance of the hydrogel in real time using the Wheatstone bridge formula as shown in the slide. We were able to observe similar trend as compared to voltage because, of course, the changing resistance is actually the driving force for the voltage. And then we did similar results for frequency testing. And now in this case, the complete cycle is a complete compression of the hydrogel and releasing of it. Now, essentially, this mimics the breathing profile because as the vest is on the infant and the baby breathes, the gel gets compressed. And then when the baby exhales, it comes back to its original position. So compression and relaxation simultaneously. And we observed dominant frequency in this case as well. And now in this case, we know we can monitor this frequency, and if the breathing profile changes, as Amr mentioned before, that the infant breathes, the cycle of the frequency is usually 3 seconds per breathing cycle. So as it deviates from this frequency, we can send an alert signal to the parents. In conclusion, we were able to get good reproducible results for chemical and mechanical properties. We also observed it through SEM images as well. We observed similar electrical properties that were shown through Wheatstone bridge and all the analysis. We were able to get real-time change in resistance of the hydrogel that leads to a difference in voltage, which is measured. And this was done by compressing the hydrogel between the two electrodes. We improved the signal-to-noise ratio to make our signal even better for even smaller change in resistance as well. And then finally, we observed the frequency, which was our main goal in order to mimic the breathing profile of an infant. Future work of the project would include implementing and integrating the entire gel in a vest, and then evaluating its performance in terms of durability and mechanically. As Amr mentioned, it has to be worn by the infant for almost 2,000 times or more during the first year. And finally, the last would be to actually measure the breathing profile of an infant. Thank you, and the floor is open for questions.
How much was the pressure you applied in your hydrogel, and how does it compare to the actual pressure an infant breathes? Okay, so when we applied the pressure, it was not significant. It needs a lot of force. Plus, we are not using exactly the same design that we'll be using an infant. An infant will be smaller and will be more significant, even a small change. Since for an infant, as he breathed, it's stretched by 3 millimeters. And that was our goal, to see a change in 3 millimeters. So what we applied by hand it's not too significant, but it was enough. So one of the issues actually we have with the thing is, it's too lightweight that sometimes over-pressing it can break it. So it's like the small amount can show resistance.
So what made you to decide to go with this hydrogel?
The polyviral? First, there was like a lot of ways to create a hydrogel from polyviral. And polyviral is one of the best conductive polymers there is. And since you can easily make it using this approach, which is green and can be easily mass produced, it was the first choice for us.
So I have a question. I imagine that the entire vest has to be somewhat elastic itself to not to constrain the baby's breathing. So did you try to do some estimates on how the elasticity of your sensor is going to play along with the elasticity of the vest itself?
Well, unfortunately, due to the time limitation, we didn't go to that step. However, as we mentioned before, our sample doesn't need that much to change. And what we found in standards for babies, that this region the force applied in this region is the highest. So we don't actually care what happens here as it stretches, but this region will make the interlock system goes in the direction we want it. So even the small change, as we proved, can give us a signal.
Right.
Plus, we'll have calibrations for each kid, so that shouldn't be a problem.
Okay. Thank you.
Okay, so about the visibility of the system, like about the gel, you're going to add it in a circuit. So this circuit is going to be mounted into the belt,
Yeah.
on the stomach.
Yes. So we'll have a basic circuit. It's not that complicated. So we'll try to convert this in a microcontroller, small microcontroller, that will do mainly all the work. And it will require low voltage because it only works when he's sleeping and it doesn't need much, just measuring the change in voltage.
So I suppose you mentioned it's going to include all this microcontroller because you need like DSP to do some MATLAB work to measure the frequency, and you need to send the frequency by wireless transmission to the smart
Yes.
or something like that. So all this is going to be included in this chip.
Yes. Yeah.
So it'll be encapsulated. It'll be encapsulated in the entire system. Yes.
And you have to take care of the current if something went wrong, because 5 volt, if the resistance went wrong, you're going to have a very large current.
True, but we are not using the 5 volts. This is for test. That is for a starting point. The goal is to go below 1 volt later.
And also, it'll be perfectly encapsulated, so there's no exposure to an infant from outside. Like, it will be perfectly insulated somehow to have it completely secured from the infant, from the body itself.
Just to add one more point, when I mentioned the cost of using the chemicals and the production itself is very minimal. Most of the cost would potentially go towards the electronic components, as you mentioned. The cost of producing one hydrogel just for testing right now is less than $1. So most of the components would be associated with the electronics, and that's where most of the cost will be.
Still have a question?
Quickly, the change in resistance from a hydrogel, what is it? Is it just your rho L by A effect, or is there something else going on?
Well, it's a basic ohmic thing. It's because the system is large enough that it follows the basic ohm resistance profile. Yeah. Yes. True.
Right. So when you press it, it has better contact for all the SEM images that Amr showed before, and that results in a better resistance as compared to the previous one.